Okay, guys. So today it's good news. This is going to be the last lecture in the thermodynamics module. All right. So we have come a pretty long way here. I think I have shown you since like the beginning of this module, you were talking about like, what is the temperature, what's the gas property of gas and all this stuff, and then heat, and then followed by the work, and then followed by the conservation of energy in general form that pretty much form the whole structure of the first law of thermodynamics. Okay, sounds cool. All right, so that was like pretty much the thing that we accomplished. And then along the way, we talked a little bit about the zeroth law, which is pretty straightforward and intuitive, talking about the thermal contact and thermal equilibrium and everything. And then toward the end, before we try to uh, look at the applications, or at least look at the processes that happen in thermodynamics, we touch upon the concepts of reversibility. Okay, so there are, a couple of things that we reach out from the first law of thermodynamics toward the second law that I'm going to conclude today. All right, so don't worry too much about the second law. I'm just going to show you what it does, or what does it mean, or what kind of thing that you can actually think of it like an extension from the first law, as like a preliminary understanding of the second law. Okay, so we're not going to dive too deeply into second law, because it is the business that takes time to understand. Plus, if you don't have enough time to understand those concepts, it's going to confuse you even more. All right, so that means I'm just going to slice a piece of second law of thermodynamics that I think is not too much to understand, and I think you guys can pick up and sort of give a good idea of what the second law is about. And I think that's serve my purpose here. Okay, so you don't have to go through like crazy stuff and understand even further. Like there are tons of terminologies that you have to learn if you want to dig deeper. Okay, all right, so before we get to that last portion, um then we're going to have one more exercise to try. Okay, and this one is going to serve as a review problems that summarize everything that you have learned so far. In terms of the first law of thermodynamics and its application. Sounds good? All right, then. Oh, there's a question about the assignments. Yes. Okay, you just submit. Yeah. You will be probably surprised like why the submission form is so short, and it's like you can pretty much write anything down. And actually that's what it is. That is true. All right, that's all I need. Okay. Where did you go last class? Sorry. I thought it was like a long weekend. It was like, I really had a week. A super long like holiday. And actually, that's true. I did. It's completely my fault. I didn't. I thought it was like a public holiday on Saturday as well. So I went out someplace. Go outside. I went to Ho Hin Cham. Just came back last night. Was that last night? No, is that right? Last night? No, on Monday night. So that's why I missed the Saturday class completely. Oh, that's totally my bad. All right, sorry. All right, if that. All right. Okay. Anyway, get back to our thermodynamics here. All right. So I'll talk to people tomorrow here. Okay. What is the thermal efficiency of an engine that operates by taking n mole of monatomic ideal gas through the circle shown in the figure? All right, so this one is sort of like a single question asking you to figure out the efficiency. All right, but along the way, of course, to be able to get to efficiency, you pretty much have to know how to calculate heat flow, right, in and out, and the difference between the heat coming in and going out. That will be the W. Okay, you guys with me? All right, so just to give you a quick summary of what we had before, was like a big diagram over here. And then you said, all right, you're going to draw in some heat from the hot reservoir. That's a Q hot. And then you're going to throw away some heat out to the cold reservoir. The difference between the two will be the work that this system can do. Okay. So once you are given a PV diagram along with the processes in there, all you need to pretty much figuring out is just what are those heats, right? Which segments in this process that give you the input to the system and which portion of this one give you an output of this system. Sounds cool? All right, so that's pretty much sort of like things that you have to calculate. All right, so let's start from the beginning here. So we're going to start from 1 to 2 segment, shall we? Yeah, sounds like fun. Yeah, okay. All right, so we go 1 to 2. And as I say, I'm going to use this one as a review. So why don't I'm going to do this? Why don't I just calculate everything that you need in the first law of thermodynamics expression? You need 3 terms, right? There are 3 terms in there. So first law of thermodynamics, say delta U equal to Q minus W. So all you need to calculate, it means if you know how to calculate all those 3, and your life would be very good. Okay. So let me sort of like review with that. So if you want, first thing is going to be the easiest from 1 to 2 is W is 0. You guys with me? Because there's no area under the curve. Cool. All right. So that's an easy part.
Okay.
Next, what about the delta U, the change in the internal energy? You said it's going to be 3/2 nR delta T. So let me put it like this. It's the T2 final temperature minus T1, the initial temperature. Okay.
Okay.
All right. So with that, then what you have over here is, all right, Ajahn, actually, even though we don't know the temperature, but nRT equal to PV all the time, PV equal to nRT, that's the equation of state of an ideal gas. So that means I can write this one as 3/2 P1V1 minus, oh, sorry, P2V2, sorry. So it's going to be P2V2 because it's an nRT at point number 2 minus P1V1. Cool?
Okay.
All right. So with that, then my delta U, or I'll just keep writing here. So it's a 3/2 P2V2. Look at point number 2 here. Pressure is 2P naught. Volume is V naught. So it's going to be 2P naught V naught minus, look at point number 1, P1V1. At point number 1, the pressure is P naught, same volume, P naught, V naught. Here we go. So at the end, what you get is 3/2 P naught, V naught. That's for the E delta U.
Okay.
All right. And once you have that, your last term is easy because it's just those 2 added together. So heat is just delta U plus W, but W is already gone. So that's what you get as well. The heat flow during the segment 1, 2 is 3/2 P naught, V naught. Cool?
Okay.
Not bad. And if you look at this one, it's like the sign is positive, guys. So when the sign is positive, what does it mean? It means heat flowing into the system. So I can draw an arrow like this, bam. And I'll just say, hey, this is 1, 2. Let me put a subscript there. So that's a Q12 heat. All right. And for those of you that just like want to jump right into this heat calculation, well, Adan, all right, because I know I'm going to try to look for the efficiency. I don't have to go through the first law of thermodynamics anymore. I just want the heat flow during segment 1, 2. What do? You can just say Q12 is NC sub V delta T. You guys remember this one, yeah?
Okay.
Because it's a constant volume process. You can write down the heat to be NC sub V delta T by knowing that C sub V is 3/2 R. See, it looks exactly the same. Bam, bam. Here we go.
Okay.
All right. So no doubt it has to be the same. Okay. But what we did in the red pen over there, that was just like showing you since the beginning of everything, starting from the work calculation, followed by the delta U calculation. The sum of the 2 will give you the heat flow. Okay. However, we already derived this one before. And that's why we got the expression of the heat flow in the constant volume process. They must be exactly the same. All right, either way. All right, so you can think of that NC sub V D delta T to be like a shortcut or something like that give you like a direct calculation to the heat during that process. Not bad, yeah?
Okay.
I don't know. I hope this kind of like works a little bit. All right. Okay, let's try one more, shall we? Okay, and after this, I can just speak freely. It's going to be pretty easy. from that point on. So let's look at 2 to 3, segment 2 to 3. All right. So I think some of you already got it. If you really want just heat, you can jump right into it. All right. But before we get to that, let me just once again show you how did we arrive to that sort of like constant pressure process. First, what is work? Work is area under the curve all the time. So from 2 to 3, the area under the curve is going to be this yellow shaded area over here. You guys with me? Yeah. All right. So that's from 2 to 3. You want that area right there. So what you get from here is it's going to be the height times the width. That's giving you the area under the curve. Plus the work done supposed to be positive because you're going from left to right. So gas is expanding. So when gas expands, so gas does work itself. So what you get is it's going to be P delta V, the height times the width. Cool. So it's going to be pressure at this level over here, and that is 2 P naught. And the delta V, all right, if you follow the agreement of the change, is a final minus initial. So it's going to be V at 3 minus V at 2 all the time. That's the change, final minus initial. And because the volume at point number 3 is 2 V naught, volume at point number 2 is V naught. So you subtract them, you get the width. So that's what you want. So it's 2 P naught times V naught, and it's positive as it's supposed to be. Gas is expanding. Cool. Alrighty. Next, what about delta U? Well, then delta U is always delta U, 3/2 NR delta T. There's no change. Ideal gas, monatomic ideal gas, follow this equation all the time. So 3/2 NR T final at number 3 minus T initial at point number 2. Okay.
Okay.
And then, of course, even though you don't have nRT, I mean, you don't have temperature, but nRT is just PV. So you can say it's going to be 3/2 P at 3, V at 3 minus P at 2, V at 2. Okay, keep going. The pressure is constant because at point 2 and point 3, they are at the same pressure. So I can say 3/2 2 P naught. I just pull common factor of the pressure out. And all I need to do is just multiply by the change in the volume, V at 3 minus V at 2. And it's the same thing. It's the width. So it's V naught again. Cool. Okay.
Okay.
And that's it, guys. So once I have that, then the Q is just the delta U plus W. So it's going to be 2 P naught V naught that I got from here, right there, plus, okay, I can cancel that, 3 P naught V naught that I got from the delta U. There you go. And that's it. So the answer is 5 P naught V naught, and it's positive.
Okay.
When it's positive means heat is flowing into my system over here. So let me erase this so you won't get confused with all the red inks there. All right, so here we go. So heat flowing in, Q23. So let me mark this one as a 2, 3. And you are done.
Okay.
Not bad, huh? Okay. And of course, for those of you that want to jump right into this heat calculation, well done. It's a constant pressure process. So it's a 5/2 NR delta T. Okay, let me write an expression first. So it's like it's an NC sub P delta T. Okay, and for monatomic ideal gas, C sub P is 5/2 R. So it's 5/2 NR delta T. And it's just 5/2 NR T at number 3 minus T at number 2. And even though you don't know the temperature, we do the same trick again. nRT is just P times V. So it's going to be, I think you know what the end of this one is 5/2 P at 3, V at 3 minus P at 2, V at 2. All right then. Okay, and that's it, guys. They're supposed to give you 5 P naught V naught exactly just like what you got right there as well. And you are done.
Okay.
Okay, so I hope by just showing you this, well, just 2 segments of this cyclic diagram, I mean, you're already in good shape. I think that's pretty much like what you're supposed to do. What else can you do when you only need 3 terms? It's either delta U, Q, or W, right? What else do you need? You don't need anything else. Okay, if you know how to calculate each one of them, and seems like at the end, heat, the Q seems to be the last to calculate. You attack W first because it's area under the PV diagram, and followed by the delta U because you know exactly how you're supposed to behave for an ideal gas. So that's kind of all right. That can be done, and then the heat follows after those two has already been calculated. Nice. All right. So you want to keep going? You can. If you want, you can follow this process, calculating the heats from 3 to 4 and 4 back to 1. But all right, because you guys sort of understand pretty much everything already at this point, so I'm going to show you. It's not a shortcut, but I think by using the understanding of the first law of thermodynamics, you don't need to do section 3 to 4 and 4 to 1. What I can do right now and right away is this, guys. You guys remember if I ask you what is the work done by this cycle, what is it going to be? We don't need this. Work done by a cycle is the area enclosed by that cycle, right? So that means it's a 1, 2, 3, 4, 1. It's a clockwise rotation. No matter what, the area enclosed is this rectangle over here. Because it's going clockwise, so the net is going to be positive work done. Okay, because on the way to the right, 2 to 3 has the area of that yellow region over there. If you go back from 4 back to 1, you're going to have to calculate the work done underneath, which is going to be negative. So think of it like you go to left to right expansion from 2 to 3. And then from 4 to 1, you do the contraction. After the contraction, the work done is like you have to just pretty much eliminate this area out. Cancel this bottom part out. You guys with me here? Just cancel that. Bam. So the area that is left is just going to be the area enclosed by this cycle, which is so easy to calculate. So I can tell you right away, the W of each cycle, okay, let me put it here. W is just going to be the width times the height. Okay, so the width is definitely the same with V naught. The height now is only 1 P naught. So it's P naught V naught. Is that cool?
Okay.
Nice. So why do we need this? Because I kind of know what's supposed to happen in the segment 3, 4, and 4, 1. Do you know what I'm saying? Look at this. Going from 1 to 2, you draw in the heat. The heat flow into the system. In 3, go to 4, you're going backward. 1 to 2, you go up. 3 to 4, you go down. So you can guess the heat in the segment 3, 4 is going to be heat flowing out. With the same reasoning, going from 2 to 3 is the expansion with the constant pressure. You draw in the heat. If you want to do 4 to 1, it's a contraction at a constant pressure. Everything is going to be reversed. So if you're not calculate heat here, it's going to be heat flowing out. But then by the conservation of energy, the incoming heat and the outgoing heat, if you do the difference has to be what? Of course, Adan, it has to be work. Does that make sense?
Okay.
So I think you don't need anything anymore because the efficiency by definition, okay, I have more space here? The efficiency is what you get over what you have to provide. What you're getting is W. What you have to provide as a heat source is, of course, which one, guys? Of course, it's going to be Q12 and Q23.
Okay.
Yeah, that's the incoming heat So Q12, Q23 serve as the Q hot flowing into your system. So that's it. What I can do is just taking the W that I already knew the answer over here. Here, okay? Plug it in there. And then I follow by Q12 plus Q23. And I got the efficiency calculated. I'm done.
Okay.
Questions? Okay, you guys sort of with me. I hope it's not too early in the morning. It's already like kind of 10 o'clock. So your brain is already get fired up. Cool. All right. However, if you don't want to use this sort of like the conservation of energy in the big picture, you can still keep going, calculating the heat from 3 to 4 and calculating the heat from 4 to 1. Yeah, that is perfectly fine. And then what you can do is you can use other expression of the efficiency if you like. So that means you can use efficiency to be 1 minus Q cold over Q hot. Yeah, that's perfectly fine. By knowing that the Q hot that you were talking about, let me highlight this. Q hot is this two dude here, the one in red. And for the Q cold, it's going to be this two dude right there, the one in blue. You will get exactly the same answer. Cool? Okay.
Okay.
And that's wrap up the first law of thermodynamics and the applications of the first law applying to some processes or some cyclic process, pretty much, that we named heat engine. Okay, you guys kind of quiet. Already, cool. All right, guys. So any questions? All right, if not, wow, that's good. So I hope you got this part, and then don't forget to try the exercises, the homework, and just practice a little bit. But as you can see, well, the only calculus that you met was just trying to find the area under the curve in the isothermal process. And that the part, well, that's none actually. So the rest of the thermodynamics, they are all algebra, all right? And of course, the algebra of tons of equations, or I mean expressions that you have to grab here and then and there and whatever, and then just put them together, all right? But in terms of the technicality of the mathematics, no, it's not that bad, all right? You don't need a lot, okay? So I hope that is some concern a little bit. All right, guys. So if you're done, that will be the main stuff that we accomplished up to this point. Now, the second stuff, and that's going to be the last thing that we're going to study in this module right here is, here we go. Let's get back to the business of the directions, okay, or the irreversibility versus reversibility of the process. So somehow you kind of like, you got it, but then, well, from what we discussed last time, I kind of understand that there are something related to reversibility, all right? And it seems like most of the stuff, or you can say like everything, is already irreversible. But the reversibility doesn't include in the first law of thermodynamics. First law of thermodynamics is just a simple equation saying that left equal to right. So this means the sum of the energy on the left is going to be equal to the sum of the energy on the right. It doesn't really help anything. So how can we quantify, or is there any like some quantities that allow us to determine if a process reversible or not? That would be so neat, right? And that would, that's, if we have that, then we can use that one to be like an indicator saying that, hey, if you can calculate this quantity over here, and this quantity will lead you to something that is reversible or something that is irreversible. Okay, and that quantity turns out to be entropy. Woohoo! All right, I don't know why I have to woohoo, but I mean, that's the name. And I think from the history, the name of the entropy was intentionally being sort of like created to rhyme, or to at least resonate with the word energy. So they was hoping that energy and entropy is supposed to be something that's come hand in hand. But you probably have already seen, it seems like we're going to spend a lot of time. We have already spent a lot of time talking about just energy, but not entropy, because it turns out it's not an easy concept to understand. And I'm going to try to explain why. It's right here, guys. So it turns out, in general, in textbooks or most of the books or whoever they want to speak about entropy, they talk about this. They talk about disorder in a system. Whoa. What does it mean? It say entropy is a measure of disorder in a system. Heat only flow in the direction that increases the disorder or randomness of the system. Now you hit another one with the word randomness. So what is going on here? All right. So just to stick with the traditional way of introducing the disorderness or the randomness of the system, let me show you this. You familiar with this? PV equal to nRT, no problem. So let's talk about the isothermal process just one more time. So it means you want to freeze the temperature. All right. So that's mean temperature is fixed. Very good. Oops, sorry. X there. All right. So temperature is fixed. So you don't have to worry about the temperature changes or anything at this point. So in this case, delta U go to 0. So from the first law of thermodynamics, Q equal to W. So check. No big deal. This is done. Now, if you want to look at the change, so that means if there's some heat flow into the system will perform a little bit of work. Cool. So all we care about right now is just, hey, I'm just taking just the magnitude at this point. Okay. Because we only want to compare them, even though the sign is already perfect. But the key is a little bit of change of the heat. So just put a little bit by putting the symbol D in front. So just to signify saying that, hey, this is a tiny bit amount of heat that flowing into the system or out of the system. And that would generate a little bit of work. So let me put a differential symbol there. It's a dW. But everyone know that this one, you can write it as a P pressure times dV. This is the definition of the work done that we introduced like first time that we saw first law of thermodynamics. Okay. So we apply PV equal to nRT. So it means the pressure is nRT over V. Cool. I plug it in there. I have nRT over V right here. And it turns out this is the term that I am interested in. It's a fractional change of the volume. What's the point? What's the point of this term? It turns out they grabbed this one and they said that this term right here implies, this one implies disorder. Whoa. Wow. Why? Why you think these terms give you the disorder of the system? The answer is, well, isn't probably not an answer, but I'll give you an analogy here. So think of it this way. You are parents, you bring your kids to a playground. Think of it that way. And then your area of your playground is just, okay, maybe you have this area here that you have to worry about your kids. You are on the sideline over here. And then you think about it. Kids will running around like crazy, right? And just, but then think of I don't know, let's say suddenly the playground over there just expand. So that means there are more places for kids to run around. So let's say that the area of the playground doubled in size. So now your kids will run even further away from you somehow, like them go crazy, right? So that's why I'm saying that it implies disorder. It's kind of sad analogy a little bit. All right, but the idea is if you think back in terms of gas, if you have gas traveling inside this room, you have some volume in this room here. And once the volume of this room increases, let's say the room is twice as big. So those gas molecules have more place to go. When they have more place to go, it means there's some, disorder means there are more place for it to go. So it means I have more trouble to keep track of all those gases and all this stuff. So that's the whole idea. So this is the reason why the increase in the volume, right, with respect to the original value will imply that you have some more disorder in your system. Cool? You buy it? Not bad, I hope. All right, so that means if you have that, I can move this nRT to the other side. So I'm just going to move this to the left. So I have the heat, I have the nRT. So that's what it is left over on the other side. Now, the term that we don't care so much is N is already fixed. We assume that the gas doesn't change in quantity. R is the constant always. So the only terms that is going to link to this dV over V is just the ratio between the heat and the temperature, guys. That's what we care about.
Okay.
And this is the one that we're going to define. So it turns out to be the heat that is flowing in or out divided by the temperature that this flow or the heat transfer is happening. We name this entropy change.
Okay.
It's the wow here, but that's no wow. This is just a definition. Yeah. All right. So the good thing about this one is, guys, we kind of hate this because heat was so hard to calculate. And now you even want to divide this by the temperature, which is, well, you have to keep track of the temperature and then you have to take the ratio. Are you sure you want this one? The answer is yes. And believe it or not, guys, this delta S here, or the change in the S here, the S is path independent.
Okay.
Wow. What does it mean? It means it has the behavior just like energy, that you don't care about the initial point. I mean, you don't care about the path that connecting the initial and your final point. All you care about is just what is your initial point, what is your final point. I can calculate the change in entropy for you. I don't care about how. I only care about what's the change. And that's what we love about energy. You don't have to tell me how, that I bring my mouse from the bottom of the screen to the top of the screen. You can do zigzag. You can move to the diagonally. You can go circle. Doesn't matter. I only care about the initial point and the final point. Entropy has this property. Isn't that cool? Yeah. All right. But the business is tough because wait. If you like this independency, I got you. Your Q, you already talked so much about heat is path dependent. Yeah. Heat is path dependent.
Okay.
So that means, so this is going to be arbitrary. I mean, this heat is going to be any numbers that you want because it depends on the path that you pick. But don't worry, it turns out you need some restriction on the heat calculation. You not just be able to just pick any heat that you want. And that's what this one is. You need a subscript R in there. You need to calculate the heat from a reversible process only.
Okay.
Okay, so it's not just any heat because we already knew heat is path dependent. So if you're going to define a heat in this expression and then you say heat can be any value, that's kind of weird, right? That's going to be bad. But the only requirement that we need for this heat is you must calculate this heat from a reversible process. What does it mean for us? It means you should be able to, not should, only you're supposed to be able to draw some diagram on a PV diagram and you calculate the heat that related to that process. If you can drag this, sort of like draw a curve or whatever from initial point to final point, then it's already guaranteed that this is a reversible process, right? Because we already said you can always flip your arrow at any time. So that means any process that can be drawn in a PV diagram must be a reversible process. If you can draw that, calculate heat from that, and then you take heat divided by temperature at each step, do the calculation, you will get the entropy change. So what does this mean? It means if someone else want to go, I want to go this. I don't care. You can calculate heat. It could be different value of the heat now, but as long as you take the ratio between the heat with respect to the temperature, you will get exactly the same delta S. Isn't that amazing?
Okay.
Wow. Wow. This is crazy. All right. But you're not going to believe me at this point. For Ajahn, are you serious? Yeah, I am serious. I'm going to show you with an example that is going to pinpoint what does this mean. All right. But anyway, the only thing that we need from here is, of course, this is a differential change. So it's mean it's just like a tiny, a super duper small change, like you just change by a little bit. You calculate the ds from that, and then you just keep going. You get another ds, and you keep changing. You get another ds, and then you keep changing. And then the ds. So this means you're just going from initial point. You do the change. And then you collect the ds, 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 until you reach the final point. You sum them all, so it's equivalent to doing the integral until you get the total change of the entropy from initial point to the final point. So this is your expression for the entropy change from one point to another, guys.
Okay.
Cool. All right. So that's the whole thing. And the good thing about this one is because S is path independent. So that means if you have a cyclic process, what does it mean? Yeah, there's no entropy change. You come back to the original position, no change. Cool. That's fun.
Okay.
All right. It's just like energy. If you come back to the original point, bam, energy is exactly the same. Same thing with the entropy. All right. So you already see the definition. You already sort of see a little bit of connections between this term and the disorder. Okay. So let's come back here. I'm going to show you how it's calculated. All right. And we're going to use this kind of thing to give you, I think it's enough for you to see or to do the connections between the entropy change and the reversibility. Okay. Remember this? Everyone remember that this is an irreversible process. No problem. No problem. Okay. And we have encountered this example, like this is maybe the third time or the fourth time already. You have a gas in insulated walls, container, everything's no heat allowed to exchange, no heat flow. Because the container is fixed, you cannot expand or contract, no work done. When there's no heat, there's no work. Total energy of the system won't change, so internal energy will not change. Let's say initially the gas is being contained in the bottom half of the container by a membrane, and suddenly membrane just breaks. So the gas fill up the whole space, the volume twice as big, the pressure reduced down in half, the temperature stays constant, no problem. All right. So this process has perfect first law of thermodynamics checked. Initial temperature, initial energy, and the final energy are exactly the same. But everyone knows, well, Ajahn, this is an irreversible process. So now I am going to show you how to calculate the entropy change of this process. Whoa.
Okay.
Are you ready for this? Exciting? Is this exciting? I don't know. It's kind of sad here. Okay, but anyway. All right. So what do we do, guys? How can you calculate this delta S? What do you think? Just give it like, just like give a good guess here. Or what kind of like, what should we do? What should we do? I need the entropy change. So I need the heat. I need the heat, and then I have to divide it by temperature at all points before I can do the integral. So, well, that must be something here, but I need something. When I need something means I need something that I can draw on a PV diagram, shall we? That's kind of like good start. So let's do that. I have P, I have V. So Ajahn, we already know that the volume is here. The pressure, let me call it like a P naught or something. So there's an initial pressure there. So, okay. So the pressure initially is P naught. The volume initially is V. So that is your initial point, is right here. That's your initial point. What is the final point? Okay, the volume double. So you come out here 2V. And because of the equation of states, the pressure is supposed to drop in half. So your final point is supposed to be here. Okay, you get guys with me? Here comes the question. Can you draw a curve that representing this expansion of the gas? One more time. My question is this. Is it possible for you to draw a curve that's explaining this exact event? The gas expands to fill up the whole container. Is there any line, is there any curve or anything that you can use to represent this process? Need some motivation here? Just kidding. The answer is no. No. The reason for that is because this is a very good example of non-equilibrium change. You guys with me now? The full process, that was so fast. Let's say at the moment that the membrane breaks, gas is ready to just woo. That woo thing, you don't even know how to draw a curve. I said, John, it's like the woo thing is like gonna go like that, zigzag, or this is gonna like straight line, or you're gonna do a curve, or I don't know. Or I mean, it's gonna be spotty because during that quick expansion thing, I mean, the pressure might not be exactly single value for the whole container. You guys with me? For example, if I'm standing right here, right there, initially I will have zero pressure because there's no gas in here. But after a while, well, gas just about to hit me, but not yet. So during that process, I mean, what does it mean by pressure of the system? The system is still very dynamic. It's changing. It's, gas just about to go crazy and everything. So that's why I'm saying that initially to the final point, okay, from the initial point to the final point, you cannot draw a line connecting these 2 points. This process is non-equilibrium process. I hope you understand what we have been doing in the past. We were trying to do things slowly. Now we know the reason why, because we want to be able to measure all of those quantities uniformly across the system. We want the same value of the pressure. We want the same value of the temperature. We want the same value of everything. Yeah. One more time, just to clarify. What does it mean by temperature for me? Right? If I'm standing at the corner of the container, initially, probably the temperature will be some value because I made almost zero pretty much, because we have no gas, right? Nothing. It's a blank, it's a vacuum. So there's no system, let's say. Once the membrane breaks, now gas start to travel, getting close to me. It gets some energy on and on. So the temperature start to rise or what? I don't even know. Who knows? Nobody knows. So my answer for this one is you cannot draw a curve connecting between the initial point and the final point. No way. Okay, guys?
Okay.
So how are we going to do it then? That's the thing. And the answer is here, guys. Remember, every time you see a PV diagram, I'm kind of like ask you to imagine that we have an isotherm. Okay.
Okay.
And this is perfect. These 2 points must be lying on a single isotherm because they are at the same temperature. Internal energy does not change. So it means the temperature of the gas stays fixed. Okay. So how would you deal with this? I have you think for a little bit. I'm gonna just look at the clock here. I think maybe this is a good place to stop first because it's sort of like, we'll see how are we going to proceed right after the commercial here. I'm just kidding. Right after the break. Sounds like a good plan.
Okay.
All right. Think a little bit. Given that all the clue that I have already given to you, okay? We want this. We want the heat. It's path independent. Everything is reversible. Even though the process that we are looking at over here is not representable in a PV diagram, what can we do? All right, I will show you exactly how it's done after the break. Sounds good? All right, guys, let's take 10. All right, be right back. All right, guys. So before we get to anything, please vote for the exam dates one more time. I just realized, and thank you for the comments. I completely put the wrong date in the previous poll. I have no idea why. Maybe I look at the wrong month or something. That's really bad. All right, guys. So just cast your vote one more time. All right, and we'll decide exactly which dates. All right, but it's gonna be a week after this week anyway. All right, so it's almost 2 weeks from now. Okay, guys. So how are you going to do this? It's too much sound effects here. How are you going to do this? Because this process cannot be put on a PV diagram. But the good thing about the entropy that we were talking about was its path independence. So it's independence of path. So the answer is it does not matter. All you need to do is just connect the first and the final, the initial and the final states with any curve that you want. When I say any curve, what does it mean? Well, Mojan, can I do like an easy curve here? Go constant pressure followed by constant volume? Yes, you can. Can you do down first and then right? Yes, you can. Can you do diagonal? Yes, you can. Can you curve out and then curve in? Yes, you can, if you can do it, of course. All right. But the idea is it does not matter which curve you pick because we already agreed, as long as you can represent the process using the PV diagram, those processes are reversible. So here comes the trick. This is pretty much, you can consider this one as a trick because these 2 points here are the initial points and the final point lie on the same isotherm. So why do we want to go through trouble doing the heat in a kind of like a weird shape curve or whatever, while we can just connecting these 2 points using a very simple isothermal process? You guys with me?
Okay.
Because this line, that connecting point A and B, that's initial point and the final point, will eventually give you the same entropy change. Okay, and I'm going to show you right away how can we do this. The reason that we picked this one is because you can do this one very easily by, okay, first of all, you know that isothermal process does not have any entropy change, which is exactly what we loved in the beginning, right? We assume temperature is fixed. So that means your first law of thermodynamics said the heat flow equal to the work done. We did that before, and we want to do it in the dynamic way, in the sense that we want to look at the change. So we turn this into differential chain of both terms. And we already knew how to deal with the differential change of the work is a PDV. So that's it. You arrive at this one from the first law of thermodynamics, right? No problem. We already did this. You express your pressure to be nRT over V. This one is good. So you already got change of the heat. Change of the heat, that sounds really weird, but that's what I mean. It's a tiny heat that is exchanging in your system to be equal to nRT dV over V. What I can do right away is I divide through by temperature. I divide by T, divided by T. So that means my temperature cancel. And this is already my change in the entropy. It's a tiny change as well. So that's why I put the differential symbol in the front. And now I want the whole change coming from A all the way to B. So the delta S, let me write it like from A to B is going to be just, I'm going to just integrate this whole thing. Bam, bam, bam. Coming from point A to point B, or you want initial point to final point, everything will be nice. So that's what you have. T cancel, bam, bam. NR is constant. I can pull it out. You only have to integrate 1 over V dV, which you guys know how to do it. It's just log of V. So this integral will give you integral of 1 over V dV from VA to VB. But now we already knew that the volume expands to twice as big as the original value. So if you start from V, you're going to end up with 2V. So this one is going to get log of V. You put V final over V initial. So it's log 2 right there. Cool. And that's it, guys. It's NR log 2.
Okay.
That is the change of the entropy going from A to B. You're done. So this is the nice things about entropy is you have freedom to do calculation on any paths that you want. Up to you. The results will be exactly the same. But of course, we want to be smart in picking the path that allow us to calculate very easily. So this is the reason why we sort of like, okay, Ajahn, we're just going to do, isothermal process connecting initial points and the final points. Now, let's analyze what this NR log 2 is giving you. This is the entropy change and it's positive change. So it means entropy is increasing, which perfectly corresponds to what we agree in the first place. We're trying to say that, hey, you have the gas initially that allowed to occupy just the bottom half of the container, right? But then afterward, you have double the volume so the gas can go crazy, double time. So that means,
okay.
So what you have over here is you have an increasing in this order of your system, right? Or in general, you say you have more configuration. I'm just going to throw in this word over here. It's like you have more way that you can arrange your system. At first, you only have just the bottom half to arrange your gas. Now you have double the space that you can arrange your gas molecules. So it means you have, think of it like you have like a bookshelf. And let's say at first you only have like a bottom half of the shelf, so you can pretty much like put your book there. You can sort around, this start with that followed by this, blah, blah, blah. But once you have more shelves, then there's so more configuration. You might put this first half in the upper shelf. Or, you can do the arrangement as much as you want. It's more arrangements, probability, not probability, possibility. There are more ways that you can arrange your thing because you have more space. And this give you that value quantitatively. That increase in the way that you can arrange your system is bigger, is increasing by this much in R log 2. And you're probably like, what kind of thing is this? But anyway, that's what it is, in the sense that I think the point that you want to take home at this step is it's positive change. Your entropy increases. And here comes the thing. With that entropy change, and with that, the idea of the reversibility that you need to put into the heat calculation, there's actually a conclusion about the entropy. It turns out entropy must remain constant or increase. That's it. You won't have any decrease in entropy ever. This is weird, right? The thing is, entropy the best that it can do is just stay the same. Otherwise, it will go bigger and bigger and bigger. Okay. And this one actually, it links to the reason that we already talked about, the reason that we don't have 100% efficiency, because whenever you run heat engine, you create some changes. And during that changes, you try to change the temperature. There is some heat flow in and flow out. A portion of heat is one way. You cannot have it accessible to you. There are some portion of that process that you have to throw away something that you cannot bring it back. So there is an irreversibility built in. And that's why it's linked to this word. It's either constant or increasing. And because if you want to do things in a complete cycle, okay, so okay, the entropy, the best thing that it can do is just constant, right? But if you talk about in terms of the change, in terms of like how can you take energy out of your system and then perform some work done, you still have to balance between the heat flow in and heat flow out. And because you never ever gonna get zero heat discarded, so you're never gonna get 100% efficiency in an engine. They are linked somehow, right? No way that you can avoid this kind of thing. So that's why it's impossible for any process on its own to transfer heat from cooler and hotter body, because that thing will do something in reverse. And when you want to do something in reverse by itself, it turns out you're going to get a negative delta S, which is going to against the first sentence over there saying that, hey, entropy will never go smaller. So that's why the process that heat want to transfer from cold to hot will give you the negative change in the entropy, and that's not possible. So I'm saying, talking to you, I mean, you don't have to worry about this because you need a lot more time to actually dive into the detail of each one of this. But anyway, these three statements over here, it's just three ways that you can talk about the second law of thermodynamics. They are equivalent, okay? It depends on which perspective that you want to talk about. The first one, you talk about the definition of the entropy and what does it mean. The second one, you want to talk about the heat engine. And the third one, you want to talk about the reversibility of the process through heat, something like that. But anyway, conclusion that I think seems to work well for us is here. The change in the entropy, so that's your delta S, of the universe, you have to make sure that this universe doesn't really mean the actual universe, but this mean is a system plus environment. Okay, so that means everything that you are considering must be greater than zero for an irreversible process. It has to go bigger. Okay, and it's the best that it can do is it's equal to zero for a reversible process. And that's it, guy. You are
Okay.
pretty much complete the second law of thermodynamics. What I'm saying over here is you guys are getting older. Of course, right? So this is an irreversible process. What does it mean? It means you are increasing in entropy. Too bad. Okay. All right. You have a cup of water. Okay. If this is like a hot coffee, when you stand it in the table, of course, all right, you go. It's eventually it's gonna cool down. This cup of coffee cannot get hotter by itself because that's the way it goes. And this process increases the entropy because it's irreversible process. Does that make sense? Yeah, it's getting something like that. You start out like, okay, you clear up your table for study, maybe at the beginning of the trimester. And now when you use your table and then you do this, do that, I mean, your table will go, it's not in place anymore. You have to spend time, arrange them back into places. But then initially it's clean, neat. But after a while, it will get, clutter, I don't know, okay, things go disorder and everything. That's general. I mean, that's normal. That's life. So what I'm saying over here is even the real universe is expanding. The universe itself, now this is a real universe. The universe is expanding. So that means, of course, if you think in terms of the volume, if you think of it like now you have greater volume. So this means our universe actually increases in entropy because, well, this process is irreversible, I guess. Yeah. So that's why they have some sort of like a sentence or a statement saying that eventually you're going to go to the heat death of the universe, because that's the place where you increase your entropy until there's nothing else left to change anymore. And that's it. That's the end of this time. End of time. That's the end of everything. Oh, I don't know if my explanation allow you to understand the second law a little bit better, but the whole point over here is what we can conclude right here. You get a positive change in entropy. This system over here is your universe. That's it. This is your gas. You already sealed everything. So that's mean this system, I mean gas in this container is your universe. You do not have any interaction with the rest of the world. So this is very isolated system, very nice. So this is a very good example of this is our universe over here. And then by going from initial point to the final point in gas is an expansion over here. You calculated your entropy change and you got a positive change in the entropy inside this universe. So the conclusion from this is this process is irreversible. That's what my conclusion.
Okay.
Cool. All right. So in the exam, don't worry. I'm not gonna try to give you any crazier question than this one. You can consider this to be the most difficult question in the entropy problems. Okay. However, I have already prepared a couple of exercises for you to try to calculate the entropy change for some simple system, maybe just like things cooling down, there's an ice, there's a water, something like that, and try to calculate the entropy change of those and see if your result matches with what we are concluding right here, which is if your universe, yeah, have the positive change of your entropy, whatever change that you are talking about is irreversible process. That's the cool thing about this one. Very nice. All right, but before we conclude, I mean, actually, I have already concluded, but before we go, here, guys, it turns out for those of you that do computer science or computer engineer and all this stuff, here, this number 2 is very good. Very good. It's very sort of like significant in a way. The number 2 here actually turns out, if you consider this system, all right, I can do a simple one, like let's say you split this in half, right? So you can imagine that, hey, is there gas in the upper half or not? Yeah, think of it that way. No or yes. Right? So this is sort of like, this is a choice. This is like, hey, are you going to have gas in the upper half of the container or not? You have 2 choices, yes or no. So actually number 2 right here is actually 2 to the power of 1. So this is actually is like a 1-bit system for you. So this system over here of this container allow you to contain the information of something. And because it's so simple, you can only contain 2 things. It's either yes or no, true or false, 0 or 1. So imagine that if you have multiple of this, then you have more ways that you can arrange. You can be like true, false, 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 true, false, false, yes, yes, no, no. And now you start to get a logic that you already got from CPU, transistors, and everything. But the numbers that you are seeing over here will be able to be used to quantify the amount of information, guys.
Okay.
Does that make sense? So this is the reason why for those of you that eventually going to go through like information science and all this stuff, whenever you want to quantify how much of the information that you can squeeze inside a system, eventually you come back to the concepts of entropy. So the entropy will be the quantitative way that you can quantify the amount of information that contained in the system. Isn't that cool? Maybe. All right, maybe not. But anyway, so that's just in case that for those of you that want to want to pursue further in information science, all this stuff. But that's the official way of quantifying the information in the system. All right, guys, but I think this is enough for us. And I think this is going to be the slide that we're going to end our thermodynamics module, guys. And we are officially done.
Okay.
All right, so after today's, I'm going to post, I think I have one more homework problem set, I think. Let me double check. Because I want you to test your understanding about the entropy as well. So let me double check if my third problems include entropy. Okay, not yet. So I will put homework set 4, which is I thought I put it in the homework set 3, but it's not. All right. So, and then I will prepare the assignment for the homework set 3 and set 4 for you to submit. All right. But other than that, I think from the first two assignments, you probably have seen that I do not require any hard work from you whatsoever. All right. So don't forget to just submit. All right. Submit anything. We'll do. All right. We'll just collect 1 point for each assignment. All right. Okay, guys. Any questions? All right, I hope you learned something, and I hope I didn't cut the topic about the entropy too short. I hope it's just enough for you to get, a taste of what the second law is about. All right, guys. Oh, if you have no further question, I think that's it. That's all I have for you guys today. And we're gonna wait for the finalized date of our first exam, and I will have the official announcements about that exam. But it's going to be somewhere around Friday, Saturday, or Sunday of the week after this week. Okay. All right. Other than that, all right, guys, take care, and I will see you guys on Monday. All right. So there's no more long weekend, so I won't get confused anymore. All right. Could it be from morning till midnight? All right, guys. I think that's. I mean, it's like a 2 or 3 hours exam, so it's not gonna be like 12 hours exam. So my exam still just like you can complete it in 2 or 3 hours. So don't worry, you have plenty of time. Definitely, I guarantee it. All right, guys. Take care. I'll see you guys on Monday. Bye bye.